Hello, BNG 319 class. Welcome to the pre-lecture for our flipped classroom combinatorial chemistry and drug design session. So we talked about drug discovery last time. We're going to take what I said in the end of the class on Thursday and delve a little deeper and talk about how we can combine different features to make different drugs that will hopefully be effective as treatments. So let's see. What is combinatorial chemistry? So we've talked about drug discovery. We've touched upon combinatorial chemistry in a way. What it is the synthesis of millions of molecules. So we can synthesize both in silico and actually in the lab millions of different molecules based on chemical reaction mechanisms that we've studied and test their biological activity, how they are as drugs, either enzyme inhibitors, agonists, antagonists, DNA intercalators, you name it. This combinatorial chemistry is often high throughput, so usually we're using robots to do a whole bunch of different combinations. And this allows us to decrease the discovery to market time. So I showed you a slide from last time, the drug discovery lecture, that said the discovery to market time was roughly anywhere from 10 to 15 years or 10 to 14 years. We can decrease, using combinatorial chemistry, we can decrease the discovery to market time to maybe 5 to 8 years. The key here is using mixtures of components or combinations of components. So let's take a look at how that might work. Okay, so we have combinatorial chemistry and we have traditional organic synthesis. Organic chemistry, in some cases, allows us to take A and B as our reactants. We react them together and we make C, right? So it's a simple synthesis reaction. However, if we do combinatorial chemistry, we can take different A's, A1, A2, A3, up to A to the N. They can have the same functional group, but they can be different molecules. Same with B's. We can have B1, B2, B3, etc., all the way to Bn, and we can do combinations of an A and a B and get combinations of C's. And we can test those combinations of C's for their effectiveness as drugs. So instead of doing just one reaction at a time, we can take combinations or batches and test many different compounds at a time. And the mixtures that work, then we can break them down and begin to isolate the active product that we have made. So here's a simple illustration to hopefully get the point across. So we have a scaffold. In this case, we have a simple scaffold. Looks kind of like a protein in a way. It's got that amide bond. But that's neither here nor there. We have a combinatorial library where we can put different things. We can put something different in the red box versus the blue box versus the green box. And we have different reds, different blues, and different greens. And we get different combinations of these things. Like in one case, we have a circle, triangle, and a square. In another case, we have a circle, square, triangle. So it depends on the combination here. We can study mixtures of these different combinations and look for mixtures that show some activity. And then we take those mixtures and then begin to separate out the different components, the different compounds that are in those combinations. And here's another example. Here's a more realistic example that's not boxes, circles, and square and triangles. We have the molecule BZA, or benzodiazepine, right here, and we have a variety of different compounds that we can try to react and put on benzodiazepine. So we have an R1, an R2, and an R3 group, and an R4 group. So we have spaces for each of these R groups to go on, and with that we can take a bag of these combinations and make a bunch of different benzodiazepine or benzodiazepine structures and test them and see what their activity is. So we can stick a methyl indole group on the R1 spot right here. And we can see that right here in this compound. Or we could have just a hydrogen there in the R1 spot. In the R2 spot, down here in the bottom, we can have things like this cyclohexane group, the cyclohexyl group. In fact, all of these seem to have the cyclohexyl group at the R2 spot. But then we can look at the R3 spot, and again, all of these seem to have just a hydrogen there at the R3 spot. And finally, in the R4 spot, we can either put a chloride or a hydrogen group. So we can have different mixtures of reactants and make different combinations of output of products here. And we can examine these, we can look at their structures, we can see how active they are in terms of inhibiting enzyme activity or being an agonist and antagonist, etc. Just by looking at mixtures. So if we have this one set of mixtures, we can analyze that, and if we have one of these is an active compound, we can try to separate it out, and then we can try to produce just simply that drug molecule because we know how it goes together. Okay, so something to consider in terms of looking for things. And this is what we're doing. We're looking for things that work. A good phrase I heard that kind of exemplifies all this, so we can go fishing. We can go fishing with a net the size of the state of Massachusetts. However, we'll have a better chance of catching fish if we toss our net over the Atlantic Ocean than if we did over the Rocky Mountains. So, in other words, it's better to start with a general structure than rather to just pick random molecules. Because if you're picking random molecules, it might be that you are doing the equivalent of throwing a fishing net over the Rocky Mountains. You're not going to catch a whole lot of fish that way. You've got a better shot if you're tossing your net in the Atlantic. So we'll take the BZA molecule as our scaffold structure. So we have a scaffold structure, and we're putting things on the ends, on the specific R groups, and we're seeing if that combination of structures will yield something that we can use as a drug. And so there are advantages to doing this. You have the conventional strategy and the combinatorial strategy. We can look at kind of hallmarks of the different strategies. Conventional strategy, we're dealing with one molecule at a time. Like I showed you, A plus B yields C. It's one molecule. You get C as the one molecule. Combinatorially, you can do many molecules at a time. Again, like I showed you, A1, A2, B1, B2. You can do A1 plus A2. You can do A1 plus B2. You can do A2 plus B1, A2 plus B2. There's a variety of molecules you can make, and you can make them all at one time in a high throughput setting. So then, in the conventional strategy, we purify the hopefully drug compound to purity, then we test. In the combinatorial strategy, we make a bunch of molecules. We test that bunch of molecules, that mixture of molecules. We find the activity, then we purify from that mixture the active one. We can look at hundreds of molecules and maybe a month in the conventional strategy. We can look at, in combinatorial, we can look at thousands of molecules a month. Slower lead generation as a result of only looking at hundreds of molecules a month. Much faster if we're looking at more molecules in a unit of time. Conventional strategy comes with a high risk of failure. Combinatorial, you're lowering your risk of failure because of a lot of these other advantages. And that will lead to lead identification, lead compound identification. Okay, so what specifically are we going to look at in the flipped classroom activity? So first we're going to consider a chemical reaction. We're going to talk about hydrazines and hydrazones. So what is a hydrazine? Well, hydrazine looks like this. We get a simple hydrazine right here. Basically, it's NH2 bound to NH2 here. So you've got a dinitrogen bond here, and this simple hydrazine, you just have hydrogens coming off as functional groups in this hydrazine. This is called simply hydrazine. But we can have the generic hydrazine structure where we're not necessarily do we have H's, hydrogens, but we have R groups associated with hydrazines. on the hydrazine. These can be methyl groups, or they can be longer carbon chains. They can be aromatics. Depends. So we have hydrazines, but then we also have hydrazones. Now hydrazones are a little bit different because we have the nitrogen-nitrogen bond here, and in one half of the molecule we have NH2. We have what is basically an amine going on right here. But in the other half of the molecule we have N, nitrogen, double bonded to a carbon. And that gives us the rest of the structure. The carbon associated with one or two R groups in either a linear or maybe a branched fashion. And this is what hydrazones look like. So we can take hydrazines and make hydrazones. And we'll look at how we do that. So this is hydrazone formation. It's formed by the action of hydrazine on aldehydes or ketones. So it's important to have this carbonyl group here as the active group. We have the hydrazine, and in the product here we get, we have the aldehyde or ketone plus hydrazine gives us this hydrazone plus water. So it is a condensation reaction. And you can see here, this is the water that comes off, and you're left with a hydrazone. So in this case we're looking at acid aldehyde and hydrazine, and that gives us acid aldehyde hydrazone plus water. And for those of you that are mechanism buffs, here is the mechanism of hydrazone formation. So we have the nucleophile here as the nitrogen, the two electrons that are on nitrogen here on one part of the hydrazine are attacking the electrophile, the carbonyl carbon, a favorite electrophile of course. Then we see the electrons in the double bond are getting donated to the oxygen. Then we have electrons coming in and donating to the hydrogen over here. Again, then the electrons flow to this nitrogen here, giving us a transient positively charged, negatively charged Zwitter ionic intermediate there. And then we get the electrons that are in this bond here will donate to a hydrogen, a proton, and that's how the water gets kicked off. These electrons in this bond go to the nitrogen. The electrons in this bond go to forming that double bond that makes up the hydrazone here. And then we have our hydrazone right here. So it's a relatively straightforward mechanism of hydrazone formation. Okay, so the flipped classroom activity, what's that all about? So essentially we're going to do on-paper combinatorial chemistry. That's what we're up to here. So we're going to look at making hydrazones. We have a mixture of products, we have a mixture of reactants rather, with which we're going to make mixtures of products. So we have an active compound library here. We have the A's, which are the aldehydes, most of them, they're mostly aldehydes here, as you can see, and we have the hydrazines that are of different types here, and we're going to make hydrazones essentially, and then we're going to line them up, we're going to put them together and check out and see if they fit in an active site. So we have our A group and our B group, and A1 will react with B1 to give you this, A1 to B2, A1 to B3, and A1 to B1, A2 to B1, A3 to B1, etc., etc. And you can see how that plays out. Okay, so the drug target is this stylized, this stylized active site. Perhaps it's an enzyme active site where the drug is going to fit. And you can see it's got different amino acid side chains coming out. It's got one hydrophobic one here. It's got two hydroxyls here. It's got an alcoholic here, and it's got a negatively charged acidic side chain right here. And the active molecule is going to bind and interact with the amino acid side chain moieties that are present in this active site. And that's going to be the idea, and that's going to be the main thing that you're going to try to put together, is that drug drug target. Using this drug target, put the correct hydrazone in the drug target. And so what you're going to do is fit the lead compound into this enzyme. Okay, so some kind of nitty-gritty stuff regarding the flipped classroom activity. This is on paper combinatorial chemistry, as I said. I will assign groups of 4 to 6, and we'll see what the group assignments are in the next slide. We will work together to answer the questions in the packet that will be handed out in class. Also, the packet will be available electronically on my courses. Everyone will be expected to turn in an individual attempt for credit, and the credit is it's worth one homework assignment, 100-point homework assignment. So that's what is going on with that, and you will start at the beginning of class, and I will collect them at the end of class. And depending on how much time it takes for everyone, we will determine how much you'll get credit for regarding that. So if you don't answer a question, if you don't get to a question, don't worry about it. Okay, so here are the group assignments. There are 6 groups. Look for your name in the groups, and hopefully I'll see you all on Tuesday. And at the start of class on Tuesday, please first thing find people that are in your group and organize yourself into groups first thing as soon as you get into class, so you have plenty of time to work on the activity. I will be floating around the classroom, answering questions and solving disputes if necessary, but certainly answering questions regarding the activity. So hopefully it'll be a fun thing, and I look forward to interacting with you folks on Tuesday, rather.